Welcome to the class on reinforcement learning and artificial neural networks. In this video, we will look at one-step horizon problems, also called Bandit problems, which are one of the standard cases of reinforcement learning. So here is one of these slot machines that represents the one-step horizon games. It's also called a Bandit machine, and that's why these problems are called Bandit problems. So basically in this scenario, the way it's set up here, you have three buttons that correspond to three different actions. The machine is always the same, so it's always the same start condition. And then you press the button, you wait for a moment, and then it makes ding, and you either get a reward or a lot of reward or no reward at all. So this is the machine, you're in front of the machine, that's your starting state. And then you can take one of the different actions, say there are three different actions, and you have chosen to take action A1, but you could also choose to take action A2, in which case you would have this transition. And then from action A2, you will also have several possible continuations. So you could end up in different states that are all different final states. And let's call this state S1, state S2, S3, S4. So we start in the starting state and we take one of the actions, two actions or three actions. I've only drawn two, and you end up in one of the states. So there is, even if you take a certain action, which means particular, if you take action A2, it's still possible that you end in state S3 or S4. This is out of your control. And this fact is described by a probabilistic branching ratio that you make the transition from S to S4 under action A2. Or here it would be the probability on this branch here. It would be the probability that you end up in state S1 starting from state S after having chosen action A1. So now the famous Q value, one of the most central notions of reinforcement learning theory, this Q value is the expected reward for action A, such as action A1 or action A2, for a given action starting from the state S. Now, let's try to calculate this with the information I give you. Now remember that the actual reward at time t may be stochastic, and at one time step it might be just RT. The expected reward is something else. The expected reward is the expectation over all possible actual rewards when you start in a given state. For example, in state S, this is where you start. You take, for example, action A2, and you end up, for example, in action S, in state S4. And each time you record a certain reward, RT. But this reward is not always the same. It's a machine with a stochastic component inbuilt. And so you have to take the expectation over several trials. And the end result of this is then the reward under this action A2 for the transition from S to S4. Now, what we want to know is not this value, but what we want to know is the expected reward starting from this state S up here, this state S, under action A2, for action A2. And so what is this Q value? Q of S A2. So it's a value associated to this branch that links the state S with the action A2. What is this Q value? Well, this is the expectation over all rewards that you may get. And it's the expectation over the rewards given that you take action A2 in state S. And now if you compare those two, you see that the difference lies in the conditioning. For this expected reward, it's conditioned on a specific final state, whereas here for this Q value, we have to average over both possible final states. So we have to average over all possible next states. Let's do this. Let's do this. So this is sum over all possible next states. P transition probability, that's this branching ratio. Transition probability PA2 under action A2 for the transition S to S prime. And then we take the reward for this specific transition, and that's our A2 S to S prime. So this is my Q value, Q of S A2, and that's the end of the calculation. So the Q value is the expected reward starting in state S, playing action A2. And if we know the mean reward for this transition, if we know the branching ratio, then we can calculate this Q value. Now, one-step horizon games use this. So now it's the same kind of image, but with three possibilities, three actions, and this is again the reminder. That's what I just did, and this is how the Q values are defined. Now let's suppose we have calculated the new Q values. So now we know the Q values. Which action should you choose? And here is the situation. I have my starting state. I have my three different Q values. Suppose I know these. One has a value of 6, the second one a value of 2, the third one a value of 5. Your aim is to gain as much reward as possible. You know the Q values. What should you do? Well, obviously, you should take the action A star, which has the maximal Q value. So the optimal action is argmax over all possible actions of these Q values. And this basically means the best policy is a greedy policy. So in one-step horizon games, the Q value is the expected reward for the state action pair. If the Q value is known, the choice of action is super simple because you just take the action with the highest Q value. But, well, imagine you walk up to Las Vegas and say, now we had this class on reinforcement learning, and the solution is I just played the action with the highest Q value. Well, and it's just calculated. But for the calculation, I need this transition probability. And now you have a problem because you don't know the transition probabilities. And you don't know the mean reward for these transitions either. So basically, you have to estimate this by playing. And that's the business model of these casinos. You have to estimate this by trial and error. So how would you do this? Well, there's a very compact way of doing the estimation, and it's naively would think, well, I need to estimate this transition matrix, I have to estimate the mean of these rewards. However, you can do it more directly. You can estimate directly the Q values, and the Q values are the things you need. And so the rule is simple. If you get a reward that's larger than your average, then you should update your Q value and this factor in front, eta, that's called the learning rate. And what I want you to do now is that you do a naive empirical averaging. You average over K trials. K trials where you have played the same action A1. And then you ask, I have my mean out of these K trials. What happens if I play one additional trial? So pause the video now for 5 to 10 minutes and go through this. Empirical average means for this branch, for this action, you average over all the rewards that you have received for this action over the first K trials with this action. And now we include one additional trial, which means we play this action once more. And I want you to show that this leads to a specific update rule and you get a specific result for eta. And then afterwards, I want you to think what this means. What this means. What means. Can you give an intuitive explanation of this difference R minus Q that leads to the change delta Q? So that's your task. Take your time, pause the video, and then I will do it on the next slide. The Q value is the expected reward. And we say the Q value, Q of SA, is approximately the same as the empirical mean. And since it's empirical, I call it Q hat. I put a hat on the Q. It's not the real thing, not the real stochastic average, the real expectation. It's my online estimate. And now I add an index and say, after K minus 1 trials, I have a certain estimate. And these trials is not all trials. It's the trials where I play action. This specific action A. And so this Q hat, after K minus 1 plays of action A, is then just the empirical average, K minus 1, R1 plus R2 plus RK minus 1. And just a reminder, this is the second time of playing action A. That's not a total second trial because you may also want to play other actions. It's the second time of action A. And now we consider what happens if you use the same formula after K trials. So after K trials, I would have Q hat K as A, which is 1 over K, and then I have R1 plus R2 plus RK minus 1 plus RK. And this is the new thing. I say this is the new thing because this means this is in fact the same as the expression we had in the parenthesis just in the line above. So somehow this is Q hat K minus 1 SA and RK. And I say it's somehow because it's not completely true, because the normalization factor is slightly different. So let me account for this and say, okay, this term RK, this term here, it comes with a 1 over K. That's no problem. Now, this guy here comes also with a 1 over K, but then it includes a 1 over K minus 1. So I write it like this. And then if you compare this, then this is, if I plug in the Q hat from the first line here, then I get exactly back the things I had. Okay, so now that's my intermediate result. Now, how can I write this K minus 1 divided by K? I can write it as K over K minus 1 over K. So let's do this. So I have here let me write it, K over K, Q hat K minus 1 of S and A. And then I have plus 1 over K from here, RK. And then I still have a term from this part here. So I have minus 1 over K and another one of these Q hat K minus 1 of S and A. Now obviously this one can be cut out. So now let's compare. On the left hand side I have Q of SA after K trials. Here I have Q of SA after K minus 1 trials. So if I subtract those two, I just get the difference. So delta Q of SA, the difference between the two terms with the red underline, this difference is 1 over K, and I have a term RK, and I have a term minus Q hat K minus 1 of SA. And this is basically the formula that I gave you with one specification. That means the eta, the update rate, is 1 over K. So let me say this again. So we have an update rule that says I compare the reward now with the expectation I have, and then I update with a learning rate eta. And this learning rate eta should decrease over time. And for this derivation, we showed that 1 over K is a good decrease. In practice, people make it decrease somehow, not necessarily with 1 over K. Now, how can we interpret this formula? Well, the change is positive if the reward at time t is larger as my current expectation, my current estimation. If the reward is larger than the estimation, then I should increase my estimation. If the reward is smaller than my estimation, I should decrease the estimation. Now the claim is, if this equation 1 has converged in expectation, then my empirical value Q hat has the correct expectation value. And the correct expectation value is this. I will give you the proof of this first part in the next little video. Moreover, if this learning rate eta decreases, as it should, then the fluctuations of this update scheme will also decrease. So it will go, my empirical average will go to the thing where I want it to go. It will converge in expectation to the real value Q of SA. So let me sum up. Q values are an important concept, a fundamental concept. It's the expected reward for a state action pair for one of these transitions, for example, Q of SA3. So it's really attached to this branch, combination of S and action. And once the Q value is known, the choice of action is simple. You just take the action with the highest Q value. So you can just go greedy. But normally, if the Q value is not known, now if it's not known and you estimate by trial and error, that means you just play, you walk through this graph of the game, you play the game and you update with this rule. And over time, you let the learning rate eta decrease, and then we find that this iterative algorithm converges in expectation to the true value Q. The true value is the expected reward for a state action pair.